This video is about rethinking the design of multiple resonance thermally activated delayed fluorescence, or MR-TADF, emitters. The central question is whether a small singlet-triplet energy gap is truly enough to guarantee performance. The standard MR-TADF paradigm aims for high-efficiency OLEDs. The golden rule suggests that high efficiency requires a near-zero singlet-triplet energy gap, or delta EST, of less than 0.03 electron volts for efficient reverse intersystem crossing, or RISC. We synthesized the DG7 emitter, which has exceptional thermal stability. It features an extended pi conjugation and a small theoretical delta EST of 0.09 electron volts, aligning with conventional design rules. In dilute solution, DG7 showed perfect solution-state photophysics with a 100% photoluminescence quantum yield, or PLQY, and an ultra-pure green-yellow emission with a 20 nanometer full width at half maximum. Despite meeting the expected criteria for strong TADF, the reality showed zero TADF behavior in solution. This raises the question of why triplet excitons are failing to upconvert if the golden rule is met. In solid-state films, the PLQY plummeted from 100% in solution to 12 to 19%. While weak delayed fluorescence was observed, the overall efficiency collapsed due to catastrophic exciton loss. Ultimately, the DG7 device suffered from dismal efficiency, achieving only a 2.8% maximum external quantum efficiency. This confirms that a small delta EST alone is insufficient for device performance. The first culprit is the nearly identical electronic density distributions of the S1 and T1 states. This results in practically non-existent spin-orbit coupling, blocking direct T1 to S1 transitions due to El-Sayed's rule. The second culprit is the T1-T2 energy trap. Since direct T1 to S1 is forbidden, excitons must upconvert to higher triplet states. DG7's massive T1-T2 energy gap traps triplet excitons in T1, preventing RISC. Secondary culprits include aggregation-caused quenching in solid films due to DG7's rigid structure, and oxygen quenching, which drastically reduced PLQY by dissolved oxygen in the initial solution studies. A new design paradigm for MR-TADF is necessary. We must shift from solely minimizing delta EST to condensing the triplet manifold, or shrinking the T1-T2 energy gap. This bypasses El-Sayed restrictions and facilitates upconversion. The energy difference between triplet states is directly correlated with the energy splitting between the highest occupied molecular orbitals. Our strategy is to minimize the HOMO-1 energy splitting to shrink the T1-T2 gap. Homogeneous chemical symmetry can cause strong orbital overlap, creating large energy gaps. The solution is to introduce lateral chemical groups with higher donor character than the central core. This localizes the relevant orbitals, closing the energy gap. For future MR-TADF design, we must prevent aggregation by inducing steric hindrance and condense the triplet manifold by combining lateral donor groups. A small delta EST is only the starting line. A dense triplet manifold is the finish line.